First of all, happy Ramadan to all Muslim students. Hopefully, you guys are still doing okay during the second day. All right. So for today, before we start our first lecture, let's just go through some important notes or reminder for everyone. Just to check, you guys hopefully can hear my voice clearly. Hopefully, testing 1, 2, 3. Okay. So for the notes, okay, so this is the second week. Just a reminder that our first lab will be conducted next week in week 3. So kindly refer to the materials that I have posted in the Google Classroom. And also please refer to the lab 1 arrangement. So far, I think almost all students has given a feedback, and majority of the students will be coming to the lab on campus. And then next week, we will be having a sharing session with invited speaker. It is scheduled during the lecture slot, so all students it's not encouraged, but hopefully all students will be attending. So for the lab-wide arrangement, this is what I have so far. Roughly about 19 students has confirmed that they will be coming to the lab on campus, while the remaining will be basically having an online session, except for Ainul and Najiha. So I think he will be joining on campus as well, but during the Thursday slot. Okay. All right, so about invited speaker, so this is the profile of our invited speaker for next week. So he will be sharing his experience basically using CFD tools or CFD software for his work in the industry. So hopefully you all can get something meaningful from this session. Okay. All right. So I think that's it for the recap or reminder. Okay. Okay. So for today, we are going to start first with the introduction of CFD. Hopefully, last week you had a time or had a chance to look at the materials that was posted under the additional reading materials during your asynchronous session. The purpose was for you to get some ideas of what is being covered for our lecture or for our course this semester. Okay, so hopefully you guys had the chance to do that. Okay, so for today, let's start with the introduction for CFD. Okay, so roughly this is our semester plan. However, please note that the arrangement has been changed slightly. Okay, for example, okay, we are going to start for the next 1 or 2 weeks, we are going to finish the introduction to CFD. And then we are going to proceed with the, instead of free flow, this was the initial planning. We are going to go straight to the hands-on detailed applications, which is the introduction to CFD tools, NCs. We are going to learn about from the start, basically what should you do in terms of when you have a problem, how do you define the domain, and then how you proceed to define the object, the mesh quality, for example, and post-processing procedures. So today, we are going to start with the introduction. Basically, we are going to discuss the importance of CFD, why we do CFD, for example, and then after that, we are going to proceed with the CFD, then fluid flow equations, then we are going to end our semester with the discretization methods. Hopefully, we are going to cover FDM, which is finite difference method. Okay. So for fluid flows, as I mentioned before, you have covered this in fluid 2 and also fluid 1. So hopefully this will be a quick revision for everyone, which we are going to cover the continuity equations, momentum equation, and just an introduction to energy equations. So we will be covering mainly these two. Okay. All right. So let's start with our lecture. Okay. So the introduction to CFD. Let's start with a quote by James Clerk Maxwell. He's a very well-known scientist. So he said, all the mathematical sciences are founded on relations between physical laws and laws of numbers, so that the aim of exact science is to reduce the problems of nature to the determination of quantities by operation with numbers. Okay, so to summarize, basically, whatever field we are in, for example, we are doing mechanical engineering, for example, most of the problems from your studies, you can see that they are all being resolved, or at the end, all that matters is the numbers. It all end up with a set of equations which can be used to explain or to elaborate the phenomena that you are investigating. Okay, so this is what James Clerk Maxwell said. Okay, so this is an example of a valve in an engine. Basically, the operation or the flow of the fluid during intake and also during the exhaust valve. Okay, so for example, the figure on the left that you see over here, you can see when the fluid is being basically compressed and pushed into the chamber, you will have a change in pressure as well as change in temperature. Okay, so the figure on the right basically just show you the mesh, the corresponding mesh of the system. Okay, so hopefully during this course over this semester, we can learn basically how to create something similar to this, maybe not as complicated as this video, but at least you get some idea of how CFD can be used to explain phenomena or working condition that is quite impossible to be investigated by naked eye or by experimental proceeding. Okay. So this is another examples of how CFD can be used to look at the wake generated by the tidal or the wind turbine. So in this case, I think this should be tidal turbine. Okay, so we know that for in case of tidal turbine, the flow of the water or the fluid is basically is the one that pushes or rotating the turbine or giving the force for the turbine to rotate. But what we are concerned with in the tidal turbine applications is the wake generated. Okay, the wake we are going to learn later in this course. The wake is basically the region behind the turbine that experiencing a deficit or the reducing in terms of, in this case, the velocity of the inflow. So for example, if you have an inflow velocity, if you look at the color over here, roughly about, let's say 2 meters per second. So immediately behind the turbine, okay, down, we call it downstream, there is a reduction in terms of velocity. So the blue region signify a reduction. So roughly, let's say we have a reduction from 2 meters per second to roughly 1 meter per second. Okay? So by knowing this, we can better plan the arrangement of the device behind the first row of either tidal or wind turbine. So that's the power of, or the beauty of CFD. If you just look at in terms of naked eye, for example, it's almost impossible for you to see the flow or the color. That's not the color. Basically, let's say the color of the wind, for example, it's impossible to see that. So we do not know basically how the arrangement should be if we just use our naked eye. If you want to conduct experiment, for example, then just imagine if you want to deploy 50 50 turbines, for example, for that particular area. They call it a farm. Okay, if you have a large number of turbines or devices, they call it a farm. So imagine if we want to check the efficiency of 50 turbines in a farm. So if you want to do it experimentally, meaning that you have to build a prototype, whether a small scale or large scale prototype, and have to physically check them and investigate the flow. But by using CFD, as you can see over here, this is just for one turbine, we can see the clear phenomena that is happening when the turbine rotating, and also the weight. The most important part for this problem, for example, is the weight generated behind the turbine, the downstream. Okay? So then we can plan, for example, maybe the turbine, instead of, we call it a squared array, we can use staggered array, for example. The position maybe, for example, instead of too close, let's say 1 meter behind the turbine, we now can put, let's say, 2 meter from the first row for the second device. So this is just an example of the beauty of CFD, and hopefully you all will be able to basically create a solution or a post-processing output, something like this soon. Okay, all right, and this is another example. This is called the von Karman phenomena, or von Karman vortex. This is based on a real phenomena, a real physical phenomena, as you can see on the right side over here. I think this is the von Karman vortex generated, or it's not generated, basically due to the clouds, the formation of the clouds that resemble the von Karman vortex. So you can see that the CFD, in this case, okay, you have a flow around a blunt object, and the wake behind generated resembles the von Karman phenomena, or von Karman shapes vortex quite accurately. So you can see over here some of the most complicated applications, or some of the most complicated phenomena in real life is being able to be replicated using CFD software. So the purpose of today's lesson is basically just to give you an overview, the importance of CFD, but also to just keep us grounded. Basically, CFD is not basically a solution for all. We will see later, we are going to discuss later how CFD can be used to simplify a lot of engineering work, but also it is dependent on experimental as well as analytical solutions. Okay. As usual, if you got any questions, please feel free to stop me. Okay, so this is another example. Basically, I think this is basically the flow around a light bulb to see how the heat can be transferred efficiently. So this is just another example how CFD can be used to simplify our work. Okay. All right. Just something for you to ponder. I'll give you about 10 seconds to read this cartoon. Okay. So what I like about this cartoon is it says if you are able to do something, I think for majority of the students taking this course this semester is also enrolling in FYP2, and also they are doing some sort of simulation for the FYP work. So when you are using CFD tools, okay, in this example, let's just say NCs. If you are able to use NCs, for example, it doesn't mean you are an expert in that particular software. So this course, hopefully, what we're going to look at is basically how to verify the output that you produce from the tools. We basically, if, for example, in this case of this dog over here, if the dog drinks something, then it will come out in terms of a urine. Okay, the output will be in terms of urine. Okay, so that's something that everyone can do. But in CFD, what you put in the software, well, there will always be something coming out at the end, okay? But how do you measure the validity or the accuracy of the result that you produce? I think that's the key here. Hopefully that this course can cover that. Okay, we want to make sure that the output that we produce means something. It's not just when you put something, you get something, and that's it. Okay. All right. So another cartoon. Okay. So it all reflects again to real life. Everyone can do something, but in the end, the output that you produce, hopefully it means something for us or for the lecturers or for your work. Okay. So I think that's the gist of this cartoon. Okay. Again, similarly. Okay. So in the end, from what the three cartoons that I shared before, in the end, there is one a phrase a phrase that usually is used in IT. They call it garbage in, garbage out. So what does it mean is, if you have a garbage as an input, okay, for example, okay, you have an input over here, something, A, B, C, D, something, okay, and then you process it, okay, the output will still be garbage. So this term is quite important in CFD. Okay, I would like to emphasize this again. It relates to what I said before. Everyone can use CFD. Everyone can use CFD tools, NCs for example. But the point of using CFD is to produce meaningful output, meaningful results. Okay, so if you put garbage, okay, as your input, okay, let's say you define your boundary, okay, but you define it wrongly, then you will get some post-processing pictures, the lovely contours that you see just now. But in the end, the contour looks nice to the naked eyes, but for those who understands how the physics works, how the mathematical model works, then we know that something is not right. Okay, so hopefully from this course, you will be able to differentiate good output and bad output, okay, for the CFD process. Okay, so what is CFD basically? So it's just means computational transport phenomena. It can involve fluid dynamics, heat transfer, mass transfer, or any other processes that involve transport phenomena. Okay? So in this case, for example, for our course, we will be dealing mostly with fluid dynamics. Okay? Fluid. So movement of fluids. So CFD can pretty much simulate, we call it simulate, simulate any phenomena related to fluid dynamics, heat transfer, mass transfer, but we have to understand what is behind the tools, which will be covered in the black box later. Okay, if you just know how to use a software, but you do not understand what is happening behind the software, then it will be troublesome when we are dealing with the output or post processing, because then you will have no idea whether your output is reliable, does it make sense, or is it just the garbage? Okay. All right. So since we're dealing with fluid dynamics, as you are aware from fluid 1 and fluid 2, all fluid dynamics phenomena, transport phenomena, can be summarized into this one equation that is called Navier-Stokes equation. Okay, so the Navier-Stokes equation that is shown here, okay, this is the main equations for all fluid dynamics or fluid problems that we are going to look at for this semester or in this course. Okay, so this is again from fluid 1 and 2. So hopefully you are aware with the Navier-Stokes equation. And in the second part of the course, we are going to derive basically how can we get from the continuity equation and also the momentum equations to get to these Navier-Stokes equations. Okay, so we're going to derive that. All right. So in a sense, okay, the pretty pictures that you look here, that you produce for your work, if it can be translated into mathematical equations or governing equations, this is basically CFD. All these pretty phenomena, all these pretty contours that you look over here, this is the aerodynamics of a lobster. So as you can see over here, they are all related to the governing equations of Navier-Stokes, of the moment. This is the continuity equations, okay, conservation of mass. Okay. So behind these pretty pictures basically lies details governing equations that needs to be fulfilled before something like this can be produced. Okay. So let's continue. Okay, all right. So just to recap, okay, briefly, we were going to cover in detail later on, but just to recap, there are two types of fluids. One is called the Newtonian fluid. The other one is non-Newtonian. So for Newtonian, the fluid's viscosity is constant. Okay? So for example, we have water, mineral oil, gasoline, and alcohol. For non-Newtonian fluid, the viscosity is not constant. It changes, okay, based on temperature or pressure, for example. So an example that we have over here, we have ketchup, honey, or glue. So for example, for glue, if you notice, if you keep on stirring the glue, for example, if you have the bottle glue, the density will change. Okay? Ketchup as well, for example, it's quite gooey, for example, if it's in the bottle. But once you put it on your bread, for example, you spread it, then the viscosity changes. So that's an example of non-Newtonian fluid. Okay. So let's discuss about CFD applications where we can use CFD knowledge. Okay. All right. First of all is, of course, automobile. I think this is quite familiar to everyone in mechanical engineering because we're dealing with aerodynamics, we're dealing with drag, for example. So this is, if you notice, this is a Tesla Cybertruck. So someone did a CFD simulation just to see the drag, if I'm not mistaken, over here. Okay, so you can see here the basically the applications, the one of the examples in automobile, how CFD can be used to basically look at the aerodynamics of the object. So in this case, we have two cars at the front and the back. You can see how the wake or the flow from the front car impacting the back car. Okay, so this again relates to drag. Okay, how the contour or the shape of the car can reduce the drag. Okay, so in Formula One, for example, they want the drag to be as minimal as possible. Okay, so that they can speed up as soon as possible after the curve. So we look at drag. We also look at the airflow for aerodynamics. The one question I have over here, for example, what does the color contour signify? Okay, so if you look over here for the Tesla truck, there is no legend given. For example, over here we have velocity magnitude. So for CFD, it's very, very important to have the legend basically because it gives meaning to the color or the pretty pictures that you have over here. So for example, without the legend, for example, what we have over here, this is what we call the contour, the legend, the color contour. So without the color contour, we have no idea what is the meaning of the yellow region, what is the meaning of the blue region, for example. Okay, so it's important that we have something that contribute to the meaning of the colors produced by the post-processing object. Then CFD can also be used in aerospace industry. So for example, on the left over here, we have a simulation showing the drag happening on the landing gear of an aeroplane. On this one, this is the first full engine computation with large eddy simulation over the in the next couple of weeks, we are going to cover what does large eddy simulation means, LES. But as you can see over here, it shows detailed phenomena that is happening in the turbojet portion. For example, air is being compressed, then entering the combustion chamber, and then combustion, then the thrust at the back. So it's quite detailed. So this is just one example of how CFD can be used to basically to investigate a phenomena. Okay, and of course we can also check the drag or lift, the aerodynamics of the wings of the aeroplane. So it can also be used in biomedical. I think nowadays is quite it's not a trend, but more and more fields, for example, more and more research has been done in biomedical that looks what is happening inside our body. Okay? So in this case, for example, the simulation shows the blood flow in a patient-specific abdominal aortic aneurysm. So they can investigate basically how the aneurysm happens. And for example, on the left figures over here, we can see how, I think this is for the heart, basically how the flows into one of the valves of our hearts, how they mix together. Okay? So if you can see over here for the heart simulation, we can put a certain inlet condition, we can define the boundaries, but how do you know that the output that you get or the result that you obtain is reliable or can be published, for example? Okay, so then you have to use the CFD output that you have to be validated with the experimental data. So you cannot just rely on these pretty pictures. Okay, when you put some values, you'll get the output, then you say, okay, this is the work that I did, and this is the figures that I got. So this is how the heart behaves or the heart functions, for example. So you cannot just say that in a scientific paper. It has to be validated, for example, with experimental data. Maybe you need to build a prototype with the same domain or with the same dimension, for example, with the same inlet condition. Where you validate your output with the prototype, then you can say, oh, my result has been validated. It is within the acceptable error range. Then it can be basically, this is how the model of the height should be, for example. Okay, so you cannot just simulate something and you say, oh, this is the outcome of my research. I just accept it. So we cannot do that. Okay, and in sports as well, for example, I think as we go into the 21st centuries, more and more sports rely on computer simulation. So one example that I want to show over here, does anyone know what is being simulated over here? This round shape object, does anyone know? Okay, comment please in the chat box, or maybe you can give your response. Anyone? Golf ball. Thank you. It is a golf ball. Okay, so as you can see over here, the figure on the top over here, this is a golf ball. This is basically a golf ball without the dent, or the they call it, is it a dent or it's not? Is it the dip? Sorry, a dip. Basically, all the small shapes or small, it's not holes, but a small dent on the balls. Okay, so this is without the dip. Okay, and however, this is the golf ball with several dips on the surface. So as you can see over here, the dips basically are very important on any golf balls because it produces the turbulence in the wake. Hence, when you have a turbulence, it will basically speed up it's not rotation, what do you call it? Basically, it is when you hit the ball can go further basically because of the turbulence regime. Okay, so if you use just a normal ball without the dent or the dip, then if you hit it compared to this part of the ball, then it will not go far. So, for example, from here, from the simulation, they can just try and test it several combinations of shape or maybe the size of the dent or the dip to know what is the most efficient design that can be produced to be used for professional golfers. Okay, so that's just one example. So the one that we have over here is the drag. So for any professional cycling team, the main problem with the bicycle, okay, apart, okay, if you are if you are into cycling, you know that the cost of a bicycle can go up until 30,000, 100,000, even like 200,000-300,000 for the professional team. Okay, but bicycle alone does not influence the outcome. Okay, of course, it plays a very important part. But if you look over here, how basically the cyclist, the position of the cyclist, the angle while cycling the bicycle, it all plays a very important role. So you can see over here, the shapes or the design of the head as well plays important role in reducing the drag for the cycling team. So this is for cycling. Then this is for swimming team. If you notice, I think a few years back in the Olympic, I can't remember which one, but all of the swimmer, they wore the full body swimming suit instead of just a speedo, as normally you see for swimming competition. They use a full suit swimming suit, which basically reduces the drag in the water. Okay, so they did the simulation basically just to see how or the most important part that they need to reduce the part of the reduce the drag on the body. So this is again examples of CFD applications in sports. Okay, and then next is for the marine or the fluid structure interaction. So this is my research area, my research interest. So I'm very, very excited to discuss about this. Okay, so if you look over here, this picture, the large picture over here that we have, this shows the flow for the tidal strait with jetting using the LAS, so large eddy simulation. I will explain later what LAS means or the significance of LAS. But if you can see over here, you have basically some kind of vortex. Okay, you have a flow coming in to the strait. Okay, the flow is circling over here, and then suddenly it's being pushed through the strait. So maybe it is during the high tide. Okay? So it's being pushed, and we have a small island over here. So you can see how the velocity around the islands, okay, is split up, okay, and then it goes to the other side. Okay, now, if you look over here, this is not a small scale simulation that you look before. For example, we look at the golf ball. Golf ball is just this big. And when you look at the car probably is just what? Maybe 1.5 meters, 2 meters at most. But the pictures that you are looking at, the video that you're looking at right now, this is the island, the mainland, the real location on a map. Okay, so what this researcher, Angus Critch, he is one of my colleagues at the University of Edinburgh. So what he's trying to look at is basically how much energy or how much kinetic energy can be obtained if we were to deploy a tidal turbine in the middle of this strait. Okay, so we check, okay, basically. So if you can see over here, again, as I said, velocity contour or the legend is important. The highest velocity that can be obtained is roughly about 1.5 to 2 meters, which is in this region. So by doing this, they know instead of just putting the tidal turbines over here, okay, let's say the farm, let's say instead of just deploying, instead of just deploying the tidal turbine over here in the middle of the strait, they now know they can either put the turbines here or in this region, because at this region we have the highest kinetic energy that can be extracted to rotate the turbines. Okay, so this is what we call large scale simulation, because you are dealing with islands, real islands. Next, the figures over here, this is just a tidal turbine. So you can see this is the detail. This is again LES simulation. This is a detailed phenomena, what is happening once basically the flow passing through the turbine. Okay, you can see how this is the vortex as well as the turbulence that is happening behind the device. As well as for the submarine, okay, the design of the submarine, you know how expensive a submarine is. It can cost billions of dollars. So instead of building a prototype, so they just use a CFD simulation to see the drag or the design. How can they optimize the design of the submarine? Okay. Yeah. Other CFD applications, the one that I mentioned just now, basically just the main highlights. Of course, some other applications I'm not going to go one by one, just highlight a few. For example, in your CPU, computer processing units, we can basically simulate how the heat transfer. If you have a GPU, we have a graphic processing unit, you have a graphic card, you can test. Basically, you can see how the heat can be efficiently removed, how many fans are needed, for example, to give optimal ventilation in your CPU. And then for data center as well, you know, the data center requires a very, very low temperature because the heat produced by they call it the rack, the processing unit. So from here, we can simulate, basically, if we have several occupants, several workers in there, plus all the racks of the data center, the internet punya details. Okay, how many heats can be reduced at what cooling capacity, for example. Okay, of course, when you have a heat sink, we can also try to simulate the efficiency of your heat sink. Okay, so what else? So much, basically, there is so much applications that CFD can be used on, which I think becomes important for you to get some idea or to have a bit of knowledge going into the industry. At least you have something that says, okay, I know how CFD works and I can analyze the output and I can use CFD tools. I think that's the key here. Okay. Okay, so again, this is just a recap. What we can use CFD for: aerodynamics of the car, through pumps, internal combustion engines, unsteady flow. We have aerodynamics. For the HVACs, ventilation. HVAC is heating and cooling for the aircons. And then we have data center as well as electronic cooling. So this is just some of the fields or some of the applications that we can apply CFD to. Okay. All right. Okay, so let's take a 5-minute break. We are going to continue after 5 minutes. Thank you. Okay, so let's continue. Okay, so next, let's discuss why we need to use CFD. Okay, more importantly, the relationship between CFD with experimental procedure as well as analytical solution. Okay, so quick question for you guys: when or at which stage of design do you use CFD in all the examples that we discussed before? Okay, so please give some comments. Okay, I'm waiting for your comments. Okay, you can use the chat box or you can just unmute. Okay, at which stage do you use CFD in the examples that we discussed? Okay, so from Teva, after we're done with our detailed designing of a project, yes, okay, partly is true. So, okay, you need to have at least some information on your design, on the input, output, final design. Okay, after designing, okay, that's final design, that's true. Before we come up with a prototype, that's right, from okay, how to pronounce your name? Tiswara, hopefully that's right. Okay, all right. So thank you for the response. So basically, it should be what you said just now. All the comments that I received, that was valid. Basically, you want to do it as early as possible. Okay, but of course, after you have finalized your design with the input, with the constraint known. Okay, but more importantly, it has to be before the fabrication and manufacturing, or of course before prototype. Because for prototype, once you have the prototype, it's better to have a prototype based on the optimized solution instead of you do when you create a prototype, but and then you go back and then do simulations. Then you realize you have to do some modifications, some improvements on the prototype did. So basically, you just wasted one process stage over there. Okay, it involves cost, time, and of course, manpower. Okay, so basically, you want to do it as soon as possible when you have all the finalized data on the product. Okay, okay. So why is it needed? Okay, so one example that can be used is for system that is difficult to test through experimentation. So the example that I showed just now, in this case, for example, if a company wants to deploy turbines or a farm, okay, at any particular location, the deployment of tidal turbines, they are very, very expensive. First, because the technology itself is not mature. Okay. So secondly, not many companies are doing this now. So when you have something that is limited in supply, it means you need to be very, very confident with your design as well as your decision on the location. Okay. So for tidal turbine as well as for wind turbine, the location plays basically, I think maybe 60 or 70% of your decision, the place itself, the venue, because you want to place your device at a location that can extract the highest amount of kinetic energy. Okay. So now, how are you supposed to conduct experimental tests for something like this, for example? Can you just measure the velocity at the inlet of the straight over here on the left side, and then you measure again the inlet on the left side or on the right side? So if you do that, means you need basically thousands of measurement data in order for you to basically identify the right locations. So that's one thing. And then not just this location that you need to identify. So for example, in Malaysia itself, we are quite a small country, to be honest, but if we consider ourselves a small country in terms of the land mass, but how can you basically pinpoint the location that is suitable, for example, to deploy this tidal turbine, for example? If you want to conduct manual investigation, then it will take years, decades, or even hundreds of years, because you need to pinpoint each location or throughout the whole country. But by using data available, the tide, the incoming tide, for example, you can just simulate part of Malaysia or the region that you know has the highest velocity flow. Then you basically now, instead of the whole country, you specify your area of interest to maybe just a few hundred kilometers instead of thousands of kilometers. So this is an example of the importance of CFD. So something that is almost impossible to do through experimental work can be done by using data available. So instead of using thousands of measurement data, maybe you just need 20 or 30 measurement data along the streets to identify or to validate your CFD output. Okay? And the other reason is basically we want to quickly test the many scenarios to answer what if questions. So for example, the golf ball that we have over here. So we just discussed just now about the importance of the dent on the ball. Okay. For example, if I ask any of the students here, how many dents do you think is the optimal number for us to use on the golf ball? Can anyone answer that on the fly? Okay. I think it will be impossible. Okay. But if you are to conduct a test, basically, okay, let's say you conduct a test between, let's say, 1,000 dents versus 1,500 dents. Okay. So it answers the question, what if we increase the number of dents? What if we enlarge the size of the dent? What if we use a different design of the dents? So it answers the what if question. So instead of wasting money on prototyping procedure, for example, you need you need hard material, for example, you need to buy equipment to conduct the experiment. Now you just need one simulation to answer your question. Okay, but keep in mind, simulation software itself is quite expensive for the commercial one. Okay, just to give you some idea, for NC software, we are lucky because we are academic institution, so we get a special price. But for industry, 5 license, for example, can cost up to 200,000 ringgit. So this is just a simple to give you an overview how much NCs cost. So for academic license, it can cost hundreds of thousands. That's for academic. But if you going to buy it for industry, then the price will be more than that. Okay, so just to give you some ideas. So not to say simulation is easy. You can do everything by simulation. First, of course, you need to buy that software. But keep in mind, there are also free software. We call it open source. So in this case, if I'm not mistaken, Angus Critch, the one who did the simulation, I think he was using Fluidity, which is an open source software. But the difference between open source and also commercial software is in terms of the ease of using. For example, NCIS is quite easy because you have the GUI. You have the graphical user interface where you can just basically click some buttons. You're going to get the next button, and then you just put some value, then you get your answers, or you get your mesh, for example. But for open source, because it's free, it's more flexible. That's a good thing because you can change the code, but mostly it involves coding, and it's not as user-friendly as the commercial one. So that's, I think, one of the main difference between the commercial and the open source. Okay. So, and then the other reason why we use CFD is because probably it's faster than experiment. Most probably, okay, not all the time, but most of the time it's faster than experimental work. Okay. So we got comments from Sue here. Mostly I just subscription plan instead of permanent license. That's right. Yes, I agree. But again, because we are academic license, we are using academic license. The beauty of academic license, sometimes they have perpetual license. Perpetual means basically you can just use for a lifetime, basically. But the downside is usually for perpetual license, there's a limit on the update. I think usually once you buy it, you can just update to the latest version, maybe 2 or 3 years after that, and then you are stuck with whatever version that you downloaded last. Okay, all right. So, and the other reason why CFD is needed, it's for the entertainment industry. Okay, I'm sure all of you, okay, if not all, most of you guys have watched the Pirates of the Caribbean, for example, and then we have, anyone can remember this movie? I can't remember the name. Oh my
Ghost Rider, if I'm not mistaken.
Come again?
Ghost Rider,
Ghost
if I'm
Rider.
not mistaken.
Ghost Rider, yes, that's right. Thank you. So this is Ghost Rider. So if you see over here, anything that involves fluid, okay, and keep in mind, fire is also considered as fluid. Okay? So anything that involves fluid basically has to be simulated. Okay? And that simulation is governed by the Navier-Stokes. So if you see over here, this picture of this guy, so this is the guy who basically revolutionized the entertainment industry by introducing a modification of the Navier-Stokes equation to accommodate this exaggeration for the use of the industry. So for example, we know that it's quite impossible for us to get a whirlpool, something like this, or even we have a tire that is on fire, okay, and keep on rolling for how long. So this guy basically came out with a solution. Basically, he at a conference, I think in 1999, he basically presented his paper that basically suggested a modification of the Navier-Stokes. If you can see over here, this is his whiteboard behind him. So this equation from the Navier-Stokes, he modified to basically to be able to integrate all these basically additional parameters used in the industry. Okay, so just keep in mind what you watch on the screen. Something that involves fluid mostly can be traced back or tracked back to the Navier-Stokes equation. Okay, so we have to thank this guy because he came up with the equations that enable us to enjoy the movie so much. Okay. Okay, so the other movies that I suggest, if you are into movies and you love to see engineering applications being used in movies, Tenet basically is quite interesting. I enjoy watching Tenet, even though I have no idea at the end. I have to watch 2 or 3 more times to understand the core issues of the movie. But Tenet basically deals about in thermodynamics. It's about thermodynamics law. So if you watch it, I think you will find it quite interesting. Of course, this is a movie. You cannot say 100% of the thermodynamics law being used is fulfilled or is being observed, but at least you learn something in the class, and when you watch it, when it relates to what you know or what you have learned, I think it will be quite interesting. This is for Tenet. For Hidden Figures, basically, this is a very good movie. Basically about figures, hidden figures, basically a group of women who was the main force behind NASA in the 70s or 60s, if I'm not mistaken. But they were, it's not rejected, but they were not treated with respect. And it's all about engineering, what you learn in static, what you learn in dynamics. I think this is a very good movie for you to watch. Okay, all right. So now let's have a look in terms of the comparison between CFD and experimental investigation first. Okay, so for experimental work, if you're doing a full-scale work, let's just use one example. Tidal turbine is quite simple. Or wind turbine. Okay, I think everyone is quite familiar with wind turbine. So wind turbine, the blade, one blade, not the whole wind turbine, just one blade of wind turbine can reach up until 20 meters. Just one blade. Just imagine if the wind turbine has 3 blades. Okay, so including the nacelle part in the middle. So let's say if you're using 20 meters, nacelle part, let's say another 2 meters. So you have roughly about 40 meters in length. Okay? Not to consider the materials that you need to purchase to use. So if you're dealing with full scale, it's going to be very expensive and often impossible. Impossible here, again, for example, is in terms of the tidal turbine. Okay? If you want to deploy 50 tidal turbines, okay, it's impossible for you to try to deploy, to put everything under the sea and then just test and then realize, this is not the best location, or the design is not correct, or the arrangement is not the best. Then you decided, maybe we need to change location. So it's not impossible. It's not possible. Okay? Because the scale is expensive, it's large, okay? It costs a lot. Okay? And of course, it deals with the measurement error. Okay? For scale model, scale means basically instead of you build a 20-meter tidal blade, you now just use a 1-meter tidal blade. Okay, so that's scale from 20 to 1 meter. But most of the time, the scale is oversimplified, the scale design. Okay? So when it is simplified, it's quite difficult to extrapolate results. Okay? And of course, when you have errors, okay, you will be dealing with errors. So how do you correct the errors from the large scale into the small scale or the scale model? So that's the problem with experimental work. Expensive, okay, and it involves error. And if you use a small scale, it is oversimplified. It cannot basically represent or produce the exact physics or phenomena that is happening with the large scale device. Now, if we go to theoretical investigation, okay, for theoretical investigation, theoretical usually is the analytical, okay, an analytical solution, meaning that you need to derive something, you need to integrate something to get to the solution. The problem with theoretical is that the solution exists only for a few simple cases. If you're dealing with complex problems, let's just use one example. Tornado, for example. Okay? Thank God we don't have tornado in Malaysia. Tornado or cyclone or typhoon. Okay? If you want to simulate that, it's not simulate. If you want to derive a solution, analytical solution, what is happening at point X, Y, Z, for example, it will be almost impossible because we don't have first the data to validate what is happening at that exact location. and the derivation itself is going to be very, very complex, okay? Almost non-existent, the solution. Okay? So the analytical solution usually involve non-linear problems or several unknowns. So this unknown is the problem where you cannot solve it. Okay. So if we go back a bit on the experimental investigation, okay, the difference between model and prototype. Okay. So if model means that it is the real size, prototype or scale model is the small one. So usually what is the problem between this? We have a problem in terms of measurement effects. Okay. We have problem in terms of model effects and the scale effects. Okay. So some of the relevant information or relevant variables that is used when you are dealing with scale model is, for example, the Froude numbers. Okay, because when you want to build something from real size into a smaller size, you need to consider the change or the physics that you need to account some of the physics happening. But even with Froude numbers, you cannot 100% replicate what is happening with the large scale models. Okay, so this is the difference between CFD and experimental and also the analytical work. Okay, so to summarize, so analytical work, it only works for a really, really simple case, and mostly you have to know or you have to make some assumptions, which we're going to look later. For example, is it a control volume problem? Will it be infinitesimal model? Infinitesimal means a very, very small model. So once you get that, then you need to start working on that one particular problem. Remember, you have to work one problem at a time. So for example, this problem analytical scale, which we are going to look later for the momentum equations, how do you define? Okay, for example, if you are just looking at one direction, this is X direction, what are the forces, shear forces as well as the stress forces acting on the elements that we choose? So this is for analytical. So if it's simple, for simple cases, it might be possible. But if you are dealing with something as complicated as tornado, for example, then the solution might be impossible to get. Okay. So computational, which is CFD, what we're going to look at, can be just as accurate as experimental work, plus you can get the information cheaper. Okay. Again, cheaper here is subjective. As I said, the license itself, you have to consider the price of the license, the price of the computational equipment that you need. Okay? But in general, it is much, much cheaper in the long run compared to experimental work. For experimental work, it is limited and expensive. Okay? I give you one example again for experimental work. In Malaysia, not many people are doing tidal turbine simulation or tidal turbine work. Okay? It's not well known yet. Okay? In Malaysia, but there are research being done. Okay? Myself included, as well as several universities, for example, UTM. I've been to UTM, they call it tank, okay, water tank. They call it flume tank, where they can test the turbines or any problems related to flow of the water. Okay, so the cost to use this can range from hundreds to thousands per day. Okay, so if you want to test, for example, if you have a prototype and you want to test the efficiency of the prototype, of course you need to test at the correct facility. So you go to this facility. So then you need to pay for the equipment, for the manpower, okay, in order for you to run your test. And usually tests will run for maybe a week, 2, or maybe more. So just imagine the cost involved if you want to run experimental work. Okay? So just keep in mind the pros and the cons of each of this aspect: analytical, computational, and experimental. Experimental, accurate, but very limited and expensive. So over here, you can see the flume is not big. So if you want to test tidal turbine, for example, it has to be a scale turbine. Okay, when we have a scale turbine, then it goes back to the discussion before. You will deal with several problems in terms of the model problems, effects. Okay. Okay. So the next question: does it mean that the CFD is more superior against experimental or theoretical investigation? Okay, I think that's the question that everyone is asking now. Okay, so the answer is no. Okay. If you look over here, this is from the CFD books that I screenshot from. So this shows the 3 dimensions of fluid dynamics. It does not say CFD as fluid dynamics, meaning that in fluid dynamics, you need the combination of these 3. Okay, you need CFD, okay, computer work. You need analytical solution or theoretical solution, as well as experimental work. They are all dependent on each other. So you cannot say that CFD is the best compared to analytical solution or the experimental solution. No. Because, for example, CFD, as I said before, once you get the output in terms of the colored contour, the very, very nice looking colored contour, you have to validate that result. Okay, how do you validate that result? Usually with experimental work or maybe with analytical solution. Okay, there might be some differences, of course, that is expected because we are going to look later when we are discussing CFD tools. CFD, most of the time, it can replicate the general phenomena, but sometimes if the phenomena is too complicated, some assumptions need to be made. So when you make some assumptions, meaning that you lose some of the data. Okay, so one example that I can give right now, between the LES that we looked before, large eddy simulations, against RANS, RANS, Reynolds average Navier-Stokes equation. So these two are the main method being used in software. So ANSYS, for example, uses RANS, Reynolds average Navier-Stokes. LES is a very specific application-specific tools, meaning that if you want to look at the details of the flow, okay, you want to look at the vortexes or you want to look at the mixing behind the turbine, then you use LES because it can reproduce the turbulence happening behind the turbine. But RANS, on the other hand, okay, it can produce the general shape of the wake. Okay, it gives you the average value of the velocity of the flow. So it's not accurate for a certain application, but for a general application, it can be used. So we are going to discuss that in the next few sessions. Okay, so CFD, keep in mind, must be used along with experimental work as well as theoretical solution, because you need to validate them. Okay, so okay, so numerical solution, meaning that CFD, because it's based on numerical solution, it exists for almost any problem. Okay, remember, almost. Okay, it means getting solution at the discrete points in the domain, meaning that, okay, we are going to look later in our study. You can consider this as a grid. Okay, so on your grid, this point, the black point, is called node. So your solution is being calculated at a specific point. Okay, it's not being calculated at all the points. Okay, so it's not continuous at all locations. So the graphic or the color contour that you look just now, that is produced from the CFD work, it is based on the average value taken at each node, then being plotted as a contour. Okay, so you have to keep in mind, of course, CFD is quite powerful, but there are downsides as well. Okay, it has to be they have to complement each other between experimental work, computational, and theory. Okay, so if you look at the pro and cons, there's a short discussion. The positive of modeling is cheaper. Okay, you have a more complete information. Okay, again, keep in mind, garbage in, garbage out. Complete here is subjective. It depends on the user, and it can handle any degree of complexity as long as you have the correct input, you have a correct domain, you have a correct mesh, then your output is reliable. But if you have garbage in, then you're going to have garbage out. But the negative of modeling, it is with mathematical description, not with reality, meaning that it depends on the mathematical solution. So later, we are going to discuss basically how do you know that your calculation is completed for the CFD tools? How do you know that the iteration can be stopped? How do you know that the convergence has been reached? So you need to know that before you can accept the result. Mathematical description can be inadequate, remember, because we are dealing mostly with assumptions. Sometimes when the shape is too complex, we are going to make certain assumptions to simplify the shapes, for example. Okay, so it can be inadequate. And then you have multiple solutions. Okay, for example, you cannot just say, okay, this is my output, okay, this is the only result that exists. It can be, you can get multiple solutions, which can be a problem. Okay? And at the end of the day, always remember garbage in, garbage out. So hopefully by the end of this course, by the end of this semester, once we finish with the lab and case study, get some idea on the good practice or the good CFD techniques that can be used later on. Okay, so in summary, basically, what we are doing for CFD is to put all this under one roof. You have the physics that you want to look at. For example, in this course, we are going to focus only for the fluid flow. And since it's quite powerful, they can be used for heat flow, phase change, and so on. But we are just going to focus for just this one. Just for fluid flow. Okay? So to simulate fluid flow, you can either do experimental analysis. Okay? But we discussed that before, the pros and cons. If you want to simulate the fluid flow phenomena, there is a governing principle. This is what we're going to look at later, which is momentum equation, continuity equation, which is conservation of mass, and just a bit on the energy equation. So you need to have these governing equations or governing principles. Previously, I think Sue asked, will the governing principles for FEA or FEM will be the same as CFD? There is slight differences, which we're going to show later. Okay? So there is a mathematical equations involved behind the tools. So that's what I want to highlight for this course. You want to look at the assumptions or the feasibility of the problem. And of course, there will be errors because we make some assumptions. We cannot replicate 100%, but we have to accept, okay, this output is acceptable within the range that we decide. Okay. So for numerical solution, there are several methods: finite volume, finite elements, as well as finite difference. We are going to focus on the finite difference method. This is for numerical solutions. We have errors, stability, which we're going to touch a bit later on over the semester. Okay. Okay. Again, to recap, we covered this at the first slide. So all in all, it goes back to the Navier-Stokes equation. Okay. So we want to solve basically the Navier-Stokes equations before we get the pretty pictures that you're looking for. Okay. So if you look over here, it says here we use the plural form for this one equation. This is the Navier-Stokes equation because it represents three equations in vector form. Three equations, keep in mind. So when I ask you later on, okay, what do you understand about Navier-Stokes? You can just say Navier-Stokes is basically, it's not a summary, it's a combination of three main equations, which is based on the three fundamentals. This is the fundamentals of the physics that we looked before. So for example, we covered this. Okay, so the physics. What are the governing principles? So for the Navier-Stokes, the governing principles are mass, conservation of mass, conservation of momentum, which is Newton's second law, F equals to ma, and based on the energy conservation. That's the governing principle. So the governing equations, so that's the principle. So the governing equations that related to the three principles here. So for the mass, we are dealing with the continuity equation. For the momentum, we are dealing with momentum equations, F equals to ma. And for energy, is the energy equations. So you need to understand where the Navier-Stokes coming from, the equations. So we call it Navier-Stokes equations, plural, because it is a combination of continuity, momentum, and energy equations. Okay. All right. So now this is to answer previous question, okay, for example, from CO. So this is a sample of other governing principles. So for example, when we are dealing with chemical engineering, okay, when you want to simulate something related to chemical engineering field, the governing principle is called conservation of mass, which was discussed before. Okay, because what you have entering your volume or your let's say this is your control volume, whatever that is going inside must also comes out. So mass in, mass out, for example. For civil engineering, it based on conservation of momentum. If you remember, this is quite similar to what you learned in static. Okay, so you need to have equilibrium. So now, if you notice, what you have learned before is now being basically being used at a higher level. So CFD is just one example of it. So the next one for mechanical engineering, if you want to look at the forces acting on the car, you look at the conservation of momentum. Okay, again, this is from static. For electrical engineering, you're dealing with conservation of charge. Okay, if you have positive, negative, okay, how does it represent? What is the equilibrium of it? So this is just an example of other types of organizing principles that is being used in simulation. Okay, so if you are using a specific software that deals with the chemical engineering applications, then the main force that is used, or it's not the main force, the equations that is being used to solve any particular problem must be related to conservation of mass. Just an example of it. Okay, so this is our semester plan. Basically, just to recap again, we covered the first lecture on the philosophy of CFD. We had the introduction, the importance of CFD, whether CFD alone is useful compared to the experimental work or analytical. So hopefully you get some idea on the pros and cons of CFD and also experimental as well as analytical. So the next one, we are going to continue with the hands-on applications. But before we go to hands-on application, because we are dealing with NCs, there will be one short introduction to CFD black box, meaning that I just want to introduce what is happening behind every simulation tools. Okay, so time right now is 4:18. I think that's all for today. For the remaining of the lecture, we have about maybe half an hour. I'm going to use the slot for the asynchronous. I'm going to record the video for asynchronous and covered the remaining duration during the asynchronous session. I hope that's okay with you guys. Okay, so now I open to any questions that students may have. Anyone?
Doctor, I'm Siu.
Siu, yes, Siu, please.
It's for Cfd access fluid. It is possible to simulate the conservation of space.
Siu, could you type, because I cannot hear your voice clearly, Siu. Could you type your question? Sorry, I cannot hear your voice clearly. Okay, so Siu got a question. Anyone? And any other questions while waiting for Siu? Please, you can just type or you can just straight away unmute your microphone. Is it possible for CFD to apply the conservation of species? Okay, conservation of species meaning specific boleh tak, Siu? What type of species? Is it like mammals, reptilia? Is it that type of species? Hello, Siu? Boleh, could you please be more specific? Substance, yes. Yes, you can. You can do that. I think, if I'm not mistaken, Dr. Tan Wee Chun, I think part of his research interest is in terms of the simulation of substances like hydrogen, something, because he's simulating, I think, chemical reactions. So chemical reactions, of course, you have positive and negative ions, then. So you have different fluids as well involved. So yes, CFD can be used to simulate different species, as you mentioned this like this. Okay, thank you, Sue. Any other questions? All right. So if you got no other questions, thank you guys. So I will post the video for the asynchronous session as soon as possible before Friday, hopefully. And next week, we are going to meet again on the same time for the sharing session. Our lab sessions, they were asking about how students who are not on campus and to undergo online session. Okay, Teva, could you please be specific? What was the question? Okay, they were asking about the students who are not on campus. Okay, for students who are not on campus, I already assigned the session on Thursday. So they can basically run the simulation software, run the lab at their home, okay, and I will be basically in front of a computer and I will try to answer any questions that they may have during the session. So I still don't get what was the question about Teva. Because the requirement for students at home, they need to have computer and be able to run simulation NC software on the laptop or computer. If they cannot run the simulation at home, then they cannot do the lab. They have to come back on campus. I think I've been very, very clear about this before the semester start, as well as last week during the briefing session. If anyone's still not clear, please clarify with me right now. Okay. So on campus, I think that's straightforward. On campus, I'll see you guys on Monday, if I'm not mistaken, at the lab. Okay. So for those at home, I've given link in the Google Classroom. So you can run the lab during the slot for the lab on Thursday. And if you got any questions, I will be on standby during the lab session. But you need to be able to run the software, NC software, to be able to do the lab. Okay. All right. I think I've been clear with this. Okay. Any other questions, guys? Okay. So if not, I'm going to end the session now. Oh. All right.